This is Dreamtime Science, where we turn fascinating discoveries into bedtime companions. Tonight's journey promises something genuinely intriguing. You know what's fascinating? I've been thinking about how some metals can almost remember their shape, like they have a quiet little secret tucked inside. There's something remarkable about materials that can change, and then gently return to exactly how they were before, almost like they have a tiny memory of themselves. Tonight I'd love to share why this isn't just science fiction, but a real kind of magic happening in the world of smart materials. Your support through likes and subscriptions keeps this tranquil laboratory of knowledge glowing softly. Tell me in the comments, what scientific concept has always fascinated you? First, let's create the perfect space for learning. Cocoon yourself in comfort, release any lingering tension, and let your breath become soft and steady. Perhaps you are reclining now, the hush of the evening settling about you, and your mind is ready to be carried along currents of science and wonder. Let us allow the gaze to glide over the boundary between the stories of old, those whispered in firelight, and the marvels of modern laboratories, where metals remember and shapes are not so fixed as they appear. This is a story of transformation, of alchemy, not in the ancient sense of lead to gold, but in the new magic of matter that responds, adapts, and even seems to recall its own lost forms. Long before we ever coaxed a metal to flex and snap back at our bidding, we humans spun tales of metamorphosis. In the shadowy corners of myth, shape-shifting is a power reserved for gods, spirits, and tricksters. Picture the Greek Proteus, slipping from form to form, now a lion, now water, now flame, eluding capture by changing his very substance. Or the Norse Loki, ever the mischief maker, who could twist himself into the likeness of a mare or a salmon or a shadow at the edge of vision. In the folklore of every continent, from the Selkies of the northern seas to the skinwalkers of the desert, there is a yearning for transformation, and a fear of it too. The world of myth is restless, nothing quite stays itself, and form is a mask that can be donned or shed. For millennia, these were the boundaries. The world of matter was steady, so we thought, and the world of myth was mutable. Yet, in the span of a single human lifetime, something remarkable has happened. In the silence of research labs, where the air hums with the faint whir of instruments and the bright sharpness of possibility, scientists have conjured a new breed of materials, ones that bend, twist, and remember. Matter that learns, matter that changes, matter that, if you squint, seems to possess a memory and a will. Smart materials, we call them, though that word smart is a sly one, evoking both intelligence and the stinging surprise of something unexpected. The family of smart materials is varied and growing, but perhaps the most uncanny, the most poetic, are the shape memory metals. Within these metals, the very atoms have been taught a choreography, a pattern to follow, a secret dance that lets them shift from one shape to another, and then, as if by magic, return. Imagine for a moment a slender wire. To all appearances, it is ordinary, metallic, cold to the touch, perhaps gleaming in the light. You bend it, twist it into a coil, knot it, deform it utterly. And then, with a gentle breath of warmth, or the immersion in hot water, the wire stirs and moves. It straightens, uncurls, smooths itself out, as if some invisible hand were guiding it home. The memory is not in the mind, but in the matter itself. A memory encoded in the structure of atoms, a shape once learned and never forgotten. The first time this was witnessed, it must have seemed as miraculous as any story of a god changing form. The roots of the discovery reach back to the 1930s, but it was in the early 1960s that the phenomenon of shape memory in metal alloys was truly understood and harnessed. The tale begins with a material known as nitinol, a portmanteau of nickel-titanium naval ordnance laboratory. the place where, in 1962, a team of researchers noticed something peculiar. A strip of nickel-titanium alloy, bent and flexed, would recover its original shape when heated. It was as if the metal had a mind of its own, a preference, a fixed idea of what it ought to be. To appreciate what is happening, we must look closer, far closer, down to the scale where matter itself is a lattice of atoms, endlessly repeating. In most metals, the arrangement of these atoms is relatively rigid. Deform the metal and the atoms are displaced, bend it too far, and the structure is changed forever, the damage done. But in shape memory alloys, the atoms are arranged in such a way, so finely balanced between two different structures, that a peculiar thing can happen. At a certain temperature, the alloy prefers one arrangement, the so-called austenite phase, named for metallurgist William Austin. In this phase, the atoms are ordered, regular, as if standing at attention. Cool the alloy, and the structure shifts to the martensite phase, named for the German metallurgist Adolf Martens. Here, the atoms relax into a different pattern, one that is much more easily deformed. When the alloy is in its martensite phase, you can bend it, twist it, shape it almost as you like. The atoms slide past one another, accommodating the stress, but crucially, they do so in a way that can be reversed. The pattern is not broken, merely shifted. Then, when heat is applied and the temperature rises past a critical point, the structure snaps back into the austenite phase. The atoms march back to their original positions, dragging the whole metal along with them. The shape memory effect is not just a trick of the surface, it is a transformation written into the inner geometry of matter. This is the alchemy of the modern age, not the transmutation of elements, but the transmutation of form. The metal forgets its deformation, remembers its first shape, and insists upon returning to it. The Greeks would have seen in this a kind of soul, an essence that could not be erased. We, perhaps, see a miracle of material science, but the sense of wonder is not so different. The story of nitinol and its kin has unfolded in tandem with our growing power to peer into the heart of matter. X-ray diffraction, electron microscopy, neutron scattering, all these tools have revealed the elegance of the phase transformations that give rise to memory. The shape memory effect is not, as it might seem, a simple elasticity. In an elastic band, the force that restores the original shape is mechanical, a stretching of bonds that snap back when released. In a shape memory alloy, the change is deeper. It is a phase transition, akin to water freezing into ice or boiling into steam, but here the transition is between two solid forms, each with its own symmetry and organization. The ability to control these transformations opens up a world of possibilities. Think of a stent, the tiny scaffold placed inside a blood vessel to keep it open. Made of shape memory alloy, it can be compressed into a slender form for insertion, and then, warmed by the body's own heat, it expands to its remembered shape, supporting life from within. Or consider eyeglass frames that return to their intended form after being bent, or robotic actuators that flex and grip with a silent, fluid motion powered only by changes in temperature. Yet for all their utility, there is something almost animate about these materials. They respond, they adapt, they remember. They hint at a world in which the boundary between the living and the inanimate is not so clear-cut. In the ancient stories, the power of transformation was always tinged with ambiguity, a blessing and a curse, a gift and a danger. The shapeshifter was admired, feared, sometimes hunted. In our age, as we teach metals to remember and polymers to sense, we too must ask, what does it mean to endow matter with memory, with the capacity to change and return? The shape memory alloys are not alone in this. They are the harbingers of a broader movement in materials science, a revolution in which the dumb solidity of matter is giving way to a more responsive, almost conversational world. piezoelectric crystals that generate voltage when squeezed, polymers that change color in response to light, hydrogels that swell or shrink with humidity. Each is a step along a path toward materials that are not mere passive substrates, but active participants. The mythic shapeshifters of old were beings of transition, straddling the line between forms. Now, in the quiet chambers of the lab, we are learning to speak that language, to coax the secrets of transformation from the silence of atoms. But we must remember, the shape memory effect is not limitless. There are boundaries, written in the laws of thermodynamics and the constraints of the crystal lattice. Each time the alloy transforms, there is a cycle of energy in and energy out, a dance that cannot continue forever without loss. The memory is durable, but not eternal. Over many cycles, the metal may tire, the boundaries between phases may blur, and the crispness of the return may soften. Even in the world of smart materials, time leaves its mark. Yet for now, the effect is robust enough to dazzle and to serve. In distant space probes, antennas unfurl with a gentle heat, their deployment made possible by the silent memory of metal. In earthquake-prone buildings, braces and dampers made from these alloys flex and absorb energy, protecting lives in moments of crisis. In the fine instruments of surgery and the sturdy tools of industry, the shape memory effect is a quiet partner, a reminder that the world beneath our fingertips is not as fixed as we once believed. Still, for all the technical mastery, there remains a sense of wonder. To see a wire bent and crumpled, and then to warm it and watch it straighten of its own accord, is to glimpse the world made strange again. It is to imagine, just for a moment, that the old myths were not so wrong after all, that the power of transformation is everywhere, waiting to be awakened. Perhaps, in the hush of night, you might recall those stories of old, the Selkie slipping out of her seal skin, the magician turning from crow to man, the hero who is both and neither. And then you might think of the metals in your glasses, your car, or perhaps in the hidden machinery that keeps hearts beating and buildings standing. The world is not so still as it appears. Beneath the surface, atoms remember, and matter yearns to return. As the tale of shape memory metals unfurls, it beckons us onward, towards stranger frontiers still. For if metals can remember and change, what else might we coax from the elements? What other powers of transformation lie hidden, waiting for the right touch, the right spark of discovery? In the next act of our journey, we will leave the realm of metals behind and turn to the world of polymers, materials whose flexibility and responsiveness open yet another chapter in the saga of shape-shifting alchemy. But that is a story for another hour, when the night is deeper and the mind ready for further metamorphosis. For now, let the thought linger. The world is alive with memory, and every shape is a story waiting to return. In the quiet darkness, let your mind drift down, down, past the everyday world of the senses, to a place where the ordinary vanishes and the extraordinary nature of matter reveals itself. Here the myth of the solid, unyielding world dissolves. Here we see that even the hardest steel is composed of restless, humming entities, bound by unseen forces, always in a subtle ballet of motion and possibility. Let us begin then with an idea so familiar it rarely receives a second thought, the notion that metals are solid objects, fixed in their shape and unchanging in their structure. Touch a rail of iron, a coin of copper, a silver spoon. They feel cool and steadfast, as if their essence is permanence itself. But the truth, as science patiently reveals, is that solidity is a kind of illusion, one conjured by the vast difference between the tiny scale of atoms and the much larger world in which we live. If we could shrink ourselves, Alice-like, until the exposed skin of a nickel coin became a vast alien landscape, we would see that the atoms of metal are not nestled together in a continuous, unmoving block. They are arranged in a crystalline lattice, a repeating three-dimensional pattern, as precise and mathematical as any honeycomb. but constructed from units far, far smaller than the eye can see. Each atom vibrates in place, jittering with energy, its electrons forming the glue that binds it to its neighbors. It is this orderly arrangement, this crystal lattice, that gives metals their strength, their sheen, and, as we shall see, their remarkable memory. But what does it mean truly for a metal to remember? Memory, in our everyday sense, is the domain of minds, of brains storing and retrieving impressions of the past. Yet in the world of shape memory alloys, those rare and wonderful families of metals that can be bent and twisted, then heated to snap back into their original forms, memory finds a new meaning. It is not the memory of thoughts or images, but of structure, a memory written in the positions of atoms and the symmetries of lattices, a memory stored in the very geometry of matter itself. To understand this, we must first appreciate just how dynamic the life of an atom in a solid can be. Though the lattice seems rigid, it is, at the atomic scale, a place of continuous fluctuation. Atoms vibrate, sometimes exchanging places, occasionally wandering into imperfections, tiny gaps or misalignments in the pattern, known as defects. These defects are not flaws in the usual sense. They are essential characters in the drama of material science, granting metals their ductility, their ability to be stretched and shaped without shattering. But the true secret of shape memory lies deeper still. It dwells in the phenomenon called a phase transition, a kind of atomic metamorphosis. Most metals, when pure, have a single, stable crystal structure at room temperature. But shape memory alloys, such as the celebrated nickel-titanium alloy called nitinol, are different. They possess the rare ability to exist in two distinct crystalline phases, each with its own unique arrangement of atoms. At high temperatures, these alloys adopt a phase called austenite. In this state, the atoms arrange themselves in an orderly, symmetrical pattern, one that is typically cubic or nearly so, like a regiment of soldiers standing at attention. This is the phase in which the metal remembers its original shape, the one imprinted during manufacture. But as the alloy cools, a subtle transformation unfolds. The atoms shift, almost as if collectively agreeing to rearrange themselves. The lattice distorts, adopting a less symmetrical phase known as martensite. Imagine a dance troupe whose members, still linked hand in hand, suddenly change their positions, tilting and sliding to new spots while preserving the overall number of dancers. The pattern is different, but the group remains whole. This new phase, the martensite, has a remarkable property: it is easily deformed. The planes of atoms within this phase can glide past each other with relative ease, allowing the metal to be bent, twisted, or squashed without breaking. Yet crucially, this deformation is not like the ordinary stretching or compressing of clay or dough. In martensite, the change is almost entirely a matter of shifting the positions of atoms within each tiny region, rather than breaking bonds or creating chaos. This is called a martensitic transformation, and it is largely reversible. If the deformed metal is reheated past a critical temperature, the atoms snap back into the austenite phase, readopting their original symmetric positions. The object returns to its remembered shape, as if waking from a dream. But why does this happen? Why do the atoms behave as if they long for their original configuration? The answer, as so often in nature, is found in the interplay between energy and order. Each phase, the high-temperature austenite and the low-temperature martensite, represents a different way for the atoms to arrange themselves, each with its own balance of internal energies. At higher temperatures, the symmetric austenite is favored. The thermal energy of the atoms is sufficient to overcome the subtle stresses of perfect alignment. As the temperature drops, it becomes energetically more favorable for the atoms to adopt the slightly distorted, less symmetric martensite structure. This is not a random process, but a precise and cooperative one. The transformation sweeps through the material in coordinated waves, like a school of fish changing direction in unison. When a force bends the martensitic alloy, it encourages certain regions, called variants, to align in ways that accommodate the deformation. The atoms shift within their local blocks, creating microscopic twins and slides, but without breaking the overall integrity of the lattice. This is why the deformation can be reversed. Upon reheating, the higher energy of the atoms allows them to overcome the barriers that held them in the deformed state, and the structure reverts to the original, stress-free alignment of the austenite phase. Even more astonishing is that this transformation is not limited to the surface or a few layers of atoms. It is a collective phenomenon, involving vast numbers of atoms acting in concert. In a thin wire of nitinol, billions upon billions of atoms may participate in the shift from martensite to austenite, as if the entire wire were a single, unified organism responding to the warmth of the environment. And so, the memory of the metal is not a recollection in the human sense, but a return to a preferred state, a state encoded in the very geometry of its crystal lattice. The atoms remember not by storing information, but by seeking the arrangement that best satisfies the subtle laws of physics that govern their interactions. Yet even as we marvel at this phenomenon, we must let go of the old myth that metals are unchanging, immutable things. The world inside a metal is a world of constant motion, adaptation, and transformation. The atoms are never truly still. Even at the coldest temperatures, they vibrate in their places, driven by the irrepressible energy of the quantum world. At higher temperatures, their jostling grows more intense, and the boundaries between phases can shift and blur. In fact, the very existence of shape memory alloys is a testament to the flexibility of metals. The periodic table offers a gallery of elements, each with its own preferences for how to bond, how to stack, how to flow. When skilled metallurgists combine two or more metals in precise proportions, they unlock new possibilities, new ways for atoms to arrange themselves, and new ways for matter to behave. Consider for a moment what happens when an ordinary piece of steel is bent. Its atoms are forced out of alignment, and the stress is accommodated by the motion of defects called dislocations, tiny misfits in the lattice that can glide along certain planes. If the bending is gentle, these dislocations move and allow the material to flex. If the bending is too great, the dislocations multiply and the metal is permanently deformed. The process is not reversible. The original arrangement is lost, and the metal retains the scars of its experience. But in shape memory alloys, the transformation between martensite and austenite provides a kind of atomic reset button. The deformation is stored not as a jumble of dislocations, but as a reversible change in the arrangement of atoms across entire regions of the material. Like a puzzle that can be taken apart and reassembled, the alloy can return to its starting form, erasing the evidence of its ordeal. This remarkable property is not without limits. If the alloy is bent too far or heated too hot, the structure can be damaged. Dislocations can form, grain boundaries can shift, and the memory can be lost. But within its proper range, the alloy behaves almost magically, cycling between forms as the temperature rises and falls. What, then, does this teach us about the nature of solidity? The truth is that all solids, not just metals, are more like slow-moving fluids than we once imagined. Their atoms are always in motion, always seeking balance between the competing demands of energy and entropy. Over long enough timescales, even the hardest diamond can flow, albeit so slowly that it would take eons to notice. Yet, in the shimmering dance of atoms within a shape memory alloy, we see the potential for matter to be both steadfast and mutable. The patterns of the crystal lattice can be altered, twisted, and restored, an intricate choreography dictated by the invisible rules of thermodynamics and quantum mechanics. Some might say that the memory of metals is merely a trick of physics, an accident of chemistry and structure. But is it not a kind of memory after all, for a wire to recall its straightness, for a spring to return to its coil, for a tiny actuator to resume its precise curve in the workings of a spacecraft or a surgeon's tool? The memory is not conscious, but it is real, a record not of thoughts, but of states preserved in the symmetry of atoms. The lesson of the shape memory alloy is that matter itself is capable of transformation and return, of holding within its structure a map of where it has been and a blueprint for where it longs to be. In the next quiet moment, as you contemplate the objects around you, the keys, the coins, the rings, remember that within them too are hidden worlds of order and change, of memory and possibility. For now, let us linger a while longer within the lattice, listening to the silent music of atoms as they shift and settle, always seeking balance, always ready to respond to the touch of heat or the press of a finger. In the shadows between the planes of atoms, where order and disorder meet, a new kind of story is always waiting to unfold. And so, the journey through the memory encoded in atoms continues, leading us toward the remarkable ways these properties are harnessed in the world beyond, where the secrets of the lattice become the tools and wonders of technology. The threshold between the invisible and the visible beckons, inviting us to step forward into new realms of discovery. It is late, and the world outside hums quietly, the air thick with the promise of rest. Within this hush, let us slip into the intricate world of tools, the instruments of curiosity and ingenuity that have allowed us to probe, prod, and persuade the remarkable class of substances we call smart materials. We are voyagers now, not merely observing, but reaching out with practiced hands and keen minds to coax secrets from matter itself. The story of how we study and manipulate smart materials is, in truth, a double helix, one strand of careful observation, the other of creative intervention. The earliest tools were the senses themselves, sight, touch, and even taste, applied by ancient metallurgists and glassmakers who noticed that certain alloys and glasses responded to heat or pressure in ways that were almost magical. But as centuries unwound, the toolkit grew, refined by the slow accretion of knowledge and the bold leaps of invention. Let us stroll first through the shadowy corridors of history, where alchemists hunched over crucibles, seeking to transmute base substances into gold. Their goals were misguided, perhaps, but their methods, careful heating, cooling, mixing, and observation, laid the groundwork for the material sciences that would follow. The first smart materials, though not yet named as such, were discovered by accident or persistent tinkering. The blacksmith noticed how repeated hammering and quenching transformed iron into steel, endowing it with new strengths and flexibilities. Glassblowers, watching with wonder as their molten creations hardened into forms that could shift color with the light, stumbled upon the earliest photonic materials. In time, these empirical methods gave way to systematic study. The Industrial Revolution brought with it not only an explosion of new materials, rubbers, alloys, and plastics, but also the birth of instrumentation, thermometers for gauging heat, balances for weighing, and most crucially, microscopes for peering into the infinitesimal. Perhaps you can picture a Victorian laboratory cluttered with brass and glass, where a scientist peers down a primitive microscope at a sliver of metal, observing the way its microstructure alters after flexing or heating. Here, the first inklings of the relationship between structure and function began to emerge, and with them the notion that materials could be engineered to respond in precise ways. But let us not linger too long in the candlelit laboratories of the past. The 20th century, with its electron microscopes and X-ray diffraction, flung open the doors to a new universe of detail. Imagine, if you will, the crystalline lattice of a shape memory alloy, an intricate repeating pattern of atoms, suddenly visible, mapped not by the unaided eye, but by the scatter of invisible X-rays. By bombarding a sample with these high-energy beams and analyzing the resulting patterns, scientists could discern not just the arrangement of atoms, but how those arrangements shifted when the material was heated, cooled, or stressed. It is as if nature's own blueprints were unfurled before us, their lines drawn in the language of energy and symmetry. Of all the tools that have shaped our understanding, the microscope stands as a sentinel. The optical microscope, reliant on visible light, was soon joined by its more powerful siblings, the electron microscope, which uses a beam of electrons to resolve features thousands of times smaller than a speck of dust, and the atomic force microscope, whose delicate tip traces the invisible contours of a surface, registering the rise and fall of atoms like a blind person reading Braille. These devices have allowed us to see, quite literally, how smart materials change at the smallest scales, the twinning of crystals in a shape memory alloy, the migration of ions in an electrochromic window, the swelling and shrinking of a hydrogel as it drinks in water. But seeing is only half the story. To truly understand, to control a smart material, one must be able to measure how it responds to stimuli. Here the tools become more varied, more specialized. Consider, for example, the dynamic mechanical analyzer, a device that flexes a material rhythmically while measuring its stiffness and damping. Such an instrument is crucial for studying polymers that stiffen or soften in response to temperature, electric field, or chemical environment. Or the spectrophotometer, which shines a spectrum of light through a material and records which wavelengths are absorbed, revealing the material's changing optical properties as it transforms. In laboratories around the world, samples of smart materials are subjected to a symphony of tests, heated in ovens with precisely controlled temperatures, stretched by tensile testers that measure how much force is needed to deform them, bombarded with magnetic fields, electric currents, or pulses of light. The data gathered from these experiments are fed into computers, which model the material's behavior, seeking patterns, predicting future responses, and guiding the design of new compositions. As our understanding has deepened, so too has our ability to manipulate these materials, not just to observe their responses, but to engineer them at the most fundamental level. Here, the tools of transformation become almost alchemical in their power. Consider the process of doping, in which tiny amounts of foreign atoms are introduced into a material's structure to alter its properties. This is the secret behind the color-changing marvels of electrochromic glass. By adding just the right impurities to a thin layer of metal oxide, scientists can create windows that darken in response to an electric current, shading a room from the sun's glare. Then there is the art of thin film deposition, a technique that allows for the creation of layers just a few atoms thick. In a vacuum chamber, materials are vaporized and allowed to condense on a surface, building up films with exquisitely tailored properties. This is how the conductive polymers in flexible electronics and the piezoelectric layers in sensors and actuators are crafted. The control here is almost surgical. The rate of deposition, the temperature, the composition, all must be tuned with precision, for a single misplaced atom can spell the difference between brilliance and failure. Nanotechnology, too, has entered the stage, bringing with it a new suite of tools. With electron beam lithography, scientists can inscribe patterns mere nanometers wide onto a substrate, creating circuits and structures with unprecedented delicacy. Scanning tunneling microscopes can not only image atoms, but move them one by one, assembling nanoscale machines or arranging conductive pathways to create materials with novel electromagnetic properties. To manipulate smart materials on these scales, researchers employ not just physical tools, but also the invisible hand of chemistry. Self-assembly, a process borrowed from nature itself, allows molecules to arrange themselves into complex structures, guided by the subtle push and pull of intermolecular forces. In the laboratory, chemists can design molecules that snap together like Lego bricks, forming gels that swell in response to pH, or crystals that twist in the presence of light. The trick lies in understanding the rules that govern these interactions, and then setting the stage so that the desired structure emerges, as if by magic, from chaos. The tools of study and manipulation are not confined to the laboratory. Increasingly, scientists deploy their instruments in the field, monitoring how smart materials perform in the real world. Sensors embedded in bridges or aircraft wings measure strain and temperature, feeding data wirelessly to engineers who can detect problems before they become catastrophes. In medicine, tiny implants made of shape memory alloys or responsive polymers are tracked in vivo, their behavior mapped in real time using MRI, ultrasound, or infrared imaging. These data streams are sifted and analyzed with the help of machine learning algorithms, which can spot subtle patterns invisible to the human eye, suggesting new avenues for exploration. One of the most extraordinary developments in recent years has been the rise of computational tools, simulations that allow scientists to predict the behavior of smart materials before they are ever made. Using the principles of quantum mechanics and molecular dynamics, researchers can model how atoms and molecules move, interact, and rearrange under different conditions. These virtual experiments can run through millions of possibilities in the time it would take to synthesize and test a single sample in the lab. The computer, in this sense, has become both microscope and crucible, a place where new materials are born in silico, their properties mapped and optimized before a single atom is touched in the physical world. Yet for all our sophistication, there remains an element of artistry, of intuition, in the manipulation of smart materials. The most advanced instruments, after all, are only extensions of the human mind, amplifying our senses, our dexterity, our imagination. The scientist at the bench, adjusting a dial or peering at a screen, is heir to the same curiosity that drove ancient metallurgists and glassblowers. It is this blend of rigor and wonder, of method and invention, that propels the field forward. In the realm of smart materials, the boundaries between study and manipulation blur. Many tools serve both purposes at once. A laser may be used to probe the internal structure of a photonic crystal or to trigger a phase change in a shape memory polymer. Magnetic fields can be applied to measure the susceptibility of a magnet or geological fluid or to induce its dramatic thickening. The interplay of stimulus and response, of measurement and control, is a dance, and the tools are its instruments, delicate, powerful, and ever-evolving. Let us pause for a moment, then, and listen to the quiet hum of a laboratory at night, long after the researchers have gone home. Under the soft glow of monitors and the faint whir of pumps, experiments continue without human oversight. Automated systems cycle through thousands of tests, varying parameters, collecting data, adjusting protocols in search of the next breakthrough. Robotic arms prepare samples, lasers sweep across surfaces, and sensors log every nuance of response. The tools themselves have grown smart, adapting and learning, accelerating discovery beyond what any single human could achieve. But even as these instruments grow in complexity, the heart of the enterprise remains unchanged, a quest to understand, to harness, to transform. Each new tool, each technique, is a rung on the ladder of progress, a means of reaching higher, seeing further, shaping matter to meet our needs and dreams. The journey is ongoing, the possibilities as boundless as our imagination. And so, in this quiet hour, as thought drifts and the boundaries between waking and dreaming soften, let us consider the horizon ahead. The tools of transformation have brought us far, but the materials themselves beckon with new mysteries. What happens, you might wonder, when these responsive substances are woven together, when their individual powers are combined and amplified? What new forms, what emergent behaviors might arise from their union, not just as passive responders, but as active participants in the systems that shape our world? This is the question that awaits, shimmering at the edge of consciousness, drawing us onward into the next chapter of discovery. How curious it is to lie under the hush of dusk and contemplate the hidden kinship between the human spirit and the world of mutable metals. In the hush of these reflective hours, when the clamour of daily necessity retreats, we may pause to sense the subtle dance unfolding between ourselves and the materials we have coaxed into newfound cleverness. There is a peculiar intimacy in the way we invite the elements to shape our world, a silent conversation that has grown ever more complex with the advent of smart materials, those metals and compounds that seem to possess, in their shimmering depths, a fragment of our own longing for adaptability, resilience, and transformation. Let your thoughts drift over the quiet surfaces of memory, recalling perhaps the first time you witnessed a shape memory alloy spring obediently into its predetermined form, as though it harboured a secret intention. Or maybe your mind wanders further back to the ancient fires where copper was coaxed from green ore, the elemental drama of transformation already hinting at the reciprocity that would one day define our relationship with matter. Now, in laboratories filled with silent machines, the old alchemy has become more intricate. Metals are not merely shaped, but programmed, their very latticework inscribed with the possibility of change, response, and learning. It is tempting to imagine on such an evening that there is a mirror held up between our mutable hearts and these responsive metals. For what is it to be human, if not to be adaptable, to sense the shifting winds and mould oneself to new circumstance? Since the dawn of our kind, we have pressed upon the world the imprint of our needs and dreams, carving bone and stone, weaving fibres, firing clay, and eventually smelting and alloying metals. Yet with smart materials, the story becomes richer. The materials themselves begin to answer, to anticipate, to join in the dance of adaptation. No longer mere passive recipients of our intentions, they become subtle partners, their behavior echoing the complexities of living tissue. Reflect, then, on the subtle shift in agency that this entails. When a building sheathes itself in panels of nickel-titanium alloy that flex in response to heat, when a medical implant gently alters its porosity to release medication at the whisper of a temperature change, there is a new kind of dialogue at play. The boundaries between the inanimate and animate become less clear, and we are compelled to ask, where, in this interplay, does humanity end and material begin? Who, precisely, is the maker, and who the made? Take, for example, the world of architecture. Once the sheltering edifice was fixed and static, a bulwark against the unpredictability of environment. But now, with the advent of smart facades, windows that tint themselves in response to the sun's glare, girders that sense stress and subtly redistribute their loads, walls that breathe and adapt in rhythm with the weather, we find ourselves architects not only of structures, but of systems that learn. The very skin of our buildings becomes a mutable interface, an organismic presence that listens and answers. In this, a deeper current is revealed, our desire not simply to resist nature, but to collaborate with it, to interlace our own tendencies for adaptation with those of the world around us. Within this impulse lies a philosophical conundrum. Smart materials invite us to reconsider the meaning of control and submission, of mastery and participation. Once we saw ourselves as sovereigns over inert matter, bending iron, copper or gold to our will. Now, as we imbue metals with memory, with the capacity to sense and transform, we are drawn into a more reciprocal relationship. The old dichotomy of subject and object begins to dissolve, replaced by an ecology of agency, a recognition that our inventions possess their own rhythms and logics, which we may influence but cannot wholly command. Think too of the field of medicine, where the boundaries between the body and its implements blur and dissolve. The pacemaker that responds to the subtle fluctuations of a heartbeat, the artificial joint that flexes and strengthens in response to the patient's gait, the stent that expands or contracts as the blood's temperature shifts. These are not mere objects, but companions, responsive presences that dwell within our flesh and blood. They become, in a sense, an extension of our own adaptive capacity, allowing the vulnerable body to negotiate the uncertainties of illness and age with a new resilience. This, in turn, raises questions both practical and profound. What does it mean to host another's agency within your own body? When you walk, knowing that a metallic filament is sensing the pressure of each step and adjusting itself accordingly, where do you end and the alloy begin? The boundary is no longer anatomical, but functional and behavioral. This entanglement of flesh and engineered matter suggests that our technologies are not merely tools, but partners in the ceaseless project of becoming, of growing, healing, and enduring. Yet not all implications are so intimate or benign. As with any new technology, the rise of smart materials brings with it shadows as well as light. The mutability that lends resilience may also harbor fragility. Materials that adapt might fail in unpredictable ways or respond to signals we did not anticipate. The more complex the system, the more nuanced its vulnerabilities. Security emerges as a new concern. If a building's fabric can respond to digital commands, it can also be manipulated from afar. The very intelligence we bestow upon matter becomes a site of contestation, a frontier where the intentions of many actors, human and non-human, intersect and sometimes collide. There is also the question of stewardship. To endow matter with the power to sense and respond is to assign it a kind of responsibility, and thus to take on new responsibilities ourselves. The metals that serve as the skeletons of our cities and the sinews of our machines must now be maintained, educated, even trusted. The relationship is no longer that of craftsman to clay, but of collaborators bound by a mutual dependence. In this light, every act of engineering becomes an ethical project, charged with questions about how much autonomy to grant, what behaviors to permit, and how to ensure that the partnership remains harmonious. Such reflections lead us inevitably to the natural world itself. For all our cleverness, the inspiration for smart materials is seldom purely human. Nature has always been the great teacher, shaping matter with exquisite subtlety. The tendrils of climbing plants that curl towards the sun, the skin of cephalopods that shifts in texture and hue, the bone that grows denser in response to repeated strain. In these examples we see that mutability is not a human invention, but a property woven into the fabric of life itself. Our smart alloys and polymers are, in a sense, an homage to nature's genius, a way of participating in its ancient strategies for survival and change. But there is perhaps an even deeper resonance. The quest to create intelligent materials is not only a technical project, but a philosophical one, a way of exploring our own place in the order of things. As we blur the lines between the made and the born, the synthetic and the organic, we are compelled to reconsider the hierarchy that once placed humanity above the rest of nature. Instead, we find ourselves enmeshed in a continuum of adaptation, a web of responsiveness that binds us to every living and non-living thing. The metals we program to change and learn are not so different in their essence from the bodies we inhabit. Both are gatherings of atoms, shaped by time and circumstance, imbued with the possibility of transformation. Such thoughts carry us, like a gentle tide, into a more poetic reflection. Imagine the city of the future, its towers shimmering with alloys that flex and breathe, its bridges alive with the silent communication of sensors and actuators. The streets are lined with vehicles whose skins ripple to shed heat, whose frames stiffen or soften in response to the needs of their passengers. Above, the roofs are sheathed in panels that open to the rain and close to the sun, harvesting energy with a subtlety that echoes the turning leaves of trees. In such a place, the boundary between the built and the grown becomes porous, the city itself a living thing, responsive, adaptive, ever-changing. Yet for all its novelty, this vision is rooted in something ancient. The earliest human shelters, woven branches, animal skins, walls of packed earth, were themselves mutable, shifting with the seasons, responding to the needs of their inhabitants. The difference now is not one of kind, but of degree and complexity. We have learned to speak the language of atoms, to write instructions into the microstructure of matter, to orchestrate transformations invisible to the naked eye. In doing so, we revisit the old dream of harmony with nature, seeking not to dominate, but to participate, to belong. Still, there are tensions that linger at the edges of this vision. The materials we create are shaped by our values, our desires, and our fears. Will we use them to build a world of resilience and reciprocity, or one of control and surveillance? The same alloy that flexes to protect its inhabitants from earthquake shock might, in another context, be programmed to exclude or confine. The intelligence we grant to matter carries with it the imprint of our own intentions, noble, ambiguous, or flawed. To reflect on smart materials, then, is to reflect on the kind of society we wish to build, the kinds of relationships we want to foster with each other and with the world that sustains us. Beneath these questions, the old wonder persists. There is a quiet astonishment in recognizing that the metals beneath our feet and above our heads, the shining wires and hidden filaments, are not inert, but alive with possibility. They are, in a sense, repositories of memory, not only in the technical sense, as in shape memory alloys, but in the deeper sense of holding within them the history of our encounter with the world. Every bridge or stent or adaptive window is a record of our ingenuity, our curiosity, and our longing for connection. And so, as the day yields to the hush of night, we find ourselves suspended in a moment of gentle anticipation. The mutable metals that gird our cities and heal our bodies whisper to us of futures yet unwritten, of transformations yet to come. They invite us to imagine new forms of life, new patterns of relationship, new harmonies between the human and the more than human world. In their silent, shifting presence, we glimpse the possibility of a world where agency is shared, where matter listens and answers, where the boundaries between self and other dissolve into a symphony of responsiveness. Perhaps, as sleep begins to draw its gentle veil over your thoughts, you sense the faint echo of this symphony, the hum of electrons in metals, the quiet pulse of adaptation, the promise of change. The human connection to mutable metals is at once a story of mastery and humility, of invention and listening, of shaping and being shaped. It is a story still unfolding, its next chapter awaiting the touch of dawn, the spark of curiosity, the patient work of hands and minds joined in the ancient, ongoing conversation between humanity and the living world. As our journey through the shimmering world of shape memory metals gently drifts to a close, their silent stories linger like a comet tail fading into the hush of space. May you carry this quiet wonder into your dreams, and when the stars beckon again, return with me for more Dreamtime tales of science's soft mysteries.